Okay, so I want to start looking at how the medieval Chinese mathematicians were solving systems of equations like this. I've just written it up here. I have like sucked all of the soul out of this problem, which dealt with x being related to the number of acres of good fields you buy, and y being related to the number of acres of bad fields that you buy, and this being the 10,000 acre. No, you paid 10,000 acres and bought 100. You paid 10,000 units of money, and you got 100 acres. Anyways, that's where the problem comes from. Using the symbols here is not something that they use. It's not something that we've seen many people using up until the very end of the Hellenistic mathematics. In my opinion, I don't know if I could do these problems without using the symbols. I think that's a mix of just that's what I'm used to, but also I think you have to be a lot smarter to do them without using the symbols, or a lot more, I don't know, ingenious or something, much more able to carry a lot of information in your head at a time than to use these symbols. The symbols help us abstract, so that we're not worrying about the number of fields. If you don't have those symbols, your brain just kind of has to do that on its own, which would be difficult for me. Anyways, to explain the method, though, I'm going to communicate in the way that I think is going to be best, which is, as I have been doing for the entire class, using this symbolism and the algebraic notation and the stuff like that. Anyways, so this is the method of double false position. We've seen the method of false position, which involves making a guess and using the nature of the relationship. It's a linear relationship to update the guess. That's exactly what we're going to do here, except we need to make two guesses because basically we have two unknowns. So here's what we're going to do. I'm going to say that my first guess is going to be that y is going to be equal to 98. And if y is equal to 98, this means that x has to be equal to 2. And so we're going to plug it into this equation here. We're going to get 300 times 2 plus 500 divided by 7 times 98. Okay, so let's see what this is going to be. 300 times 2 is 600. Now I chose 98 because half of 98 is 49, and 49 is 7 times 7. So then 98 is equal to 7 times 14. So this ends up being 500 times 14. 500 times 14. Now, how am I going to do 500 times 14? Well, obviously it's a lot of fun just doing this on a camera, but 500 times 14, I'm going to think about 1,000 times 14, which is going to give me 14,000, and then divide by 2, which is going to give me 7,000. And so we've got 7,600. Okay, now my next guess. My next guess is going to be, let's say y is equal to 70. And so if y is equal to 70, this means x has to be equal to 30. So if y is equal to 70, this means that x has to be equal to 30. So if I plug these in, we're going to get 300 times 30 plus 500 over 7 times 70. Okay, what are we going to get? We're going to get a 9 with 3 zeros there. 70 over 7, that's 10, so this is going to be plus 5,000. And this is equal to 14,000. Okay, so notice what we have here. With this guess right here, we get more. So this is called a surplus guess because we've put in numbers and we've gotten more than 10,000. And then this would be a deficient guess. Okay, so how can we use that? We now need to modify our guess somehow. So here's what we're going to do. We're going to come over here. And one thing that I want to point out, we're going to come over here. And because we have a linear relationship, notice what is true here. Let's say that delta x is going to be equal to the actual value of x, which is unknown, minus, I'm going to say x sub 1 for the guess. Actually, I'm going to call it x sub g for the guess. And then delta y is going to be equal to y, the actual value of y, which is unknown, minus y sub g. And then I'm going to define a function, just to keep things in the same order. It's a function of two variables, 300x plus 500 over 7 y, so just the left-hand side here. I'm going to say this is equal to z. Now observe, this is only true because the left-hand side is a linear function in x and y. It's a linear function in x and y. So what this means is that 300 times delta x plus 500 over 7 times delta y is equal to delta z. Okay, so if we forget about where this problem comes from, like all of this stuff, if I just define this function and say this is equal to delta z, then 300 times the change in delta x plus 500 times 300 times the change in x plus 500 over 7 times the change in y is going to be equal to the change in z. Okay, so because it's linear, we know that the change in z is just going to be equal to the corresponding change in delta and x and delta and y, where we just plug in delta x and delta y where we had x and y before. Okay, this only works if it's linear, for linear functions. If it's not linear in a variable, it's not going to work. Okay, so now what does this tell us? Well, because we know x plus y is 100, if we increase x by 10, we have to decrease y by 10. So what this means is delta y is just equal to delta x, if we have this constraint. In general, of course, they're independent, but if they're coupled together with this constraint right here, we know that delta y and delta x are just negatives of each other. So what I can do here is I can put a minus sign here and make this delta y a delta x. And so whatever your perspective is, if we divide both sides by delta x, what this tells us is 300 minus 500 over 7 is equal to delta z over delta x. Okay, so the ratio of the deltas is going to be constant. Okay, and it doesn't matter if we evaluate it at 1x and not x, whatever it is, we know that delta z over delta x, that ratio is going to remain constant. It doesn't depend on x, it doesn't depend on the value of z or the value of x, it's just equal, it's just constant. Okay, and this is what linearity gives us. Okay, this is one of the things that is clear that they understood this sort of proportional reasoning, just like we saw with the Egyptians. They understood this as well. Okay, so let me come over here. Okay, so let me use that as our fact there, that the ratio delta z over delta x, or as we will use it, delta x over delta z, is constant. Okay, so we've got delta x over delta z is equal to a constant. Okay, so now what this means, if you look at this in the particular case where delta x is the true value of x minus a guess, and then delta z is going to be the true value of z, which is 10,000, minus whatever we get, that's how we're going to look at it here. So if I plug in the first guess, or let's do the second guess first. Delta x, I'm going to have delta z is going to be 14,000 minus 10,000. So I'm going to have something over, let me just write it out explicitly what it is. 14,000 minus 10,000. Okay, now on the top, my guess for x here, I could use my guess for y or my guess for x. I'm going to use my guess for x here. My guess for x is 30, so it's going to be 30. That's my guess. minus x. So 30 minus x is equal to 14,000 minus 10,000. Okay, because when you plug in x, you get 14,000. When you plug in the unknown value of x, you get 10,000. Okay, now this is going to equal the following. It's going to equal the first guess up here, x is equal to 2. So it's going to be 2 minus the actual value of x. Okay, now when you plug in 2, you get 7,600. Not 76,000, 7,600 minus 10,000. Again, when x is equal to 2, the right-hand side of this function is 7,600. And then when it's equal to x, the correct value, it's by definition equal to. Okay, so if the board suddenly looks different, it's because, meaning that side of the board over there, suddenly looks different. It's because when I was writing on the board, right here, I did 7,600 minus 10,000. And in my brain, that came out to 4,000. And so I wrote 4,000 and the denominator. Now, most of you probably know that it's not 4,000 and it is instead 2,400. Anyways, well, it's minus 2,400. So we're going to have x minus 2 over 2,400. And instead of just remaking the entire video, I'm just going to go, do it like this. All right, so now what we have is we have an equation. Sorry, just double checking to make sure I have everything. We have an equation that just involves x alone. So we've got 30 minus x. Okay, now 14,000 minus 10,000. I'm pretty sure that is 4,000. And then over here, we're going to have x minus 2 over 2,400. This is an equation for x. We can solve for this. Now, saying it like this, it's pretty easy. We can just say solve for it, and we're going to get a formula for it. But again, I think it's interesting to me that this theme that we've seen throughout the semester is that they were able to do this just by describing what to do. So I'm guessing their reasoning is the proportional reasoning. Constant ratios has to be part of their idea that they're doing this, but not being able to write it out in symbols and kind of not having that same sort of thought process in terms of functions, to me, I'd be lost. Anyways, what we're going to do now is I want to get sort of a general formula for this. 30 minus x. I'm just going to call this the guess x1. x1 minus x. And I'm going to call this difference here d1. And then over here, I'm going to say x minus x2 over d2. Okay, now by doing algebra, by doing sort of simple algebra, we're going to get that x is equal to x1 times d2 plus x2 times d1 over d1 plus d2. Now, we can think about plugging in these numbers right here, and that's going to give us what x is. And then once we know what x is, we can use this formula to tell us what y is. Okay, so that is it. That is the first example that we're going to look at how the medieval Chinese mathematicians are solving systems of equations. It's a sort of more advanced version of the method of false position that we saw with the Egyptians. But again, a very important thing that they also understand is that you've got to use proportionality, and that these proportional relationships, with linearity, you get these proportional relationships to use. And so that's going to be it for this video. We're going to look at some other videos of other techniques that they have and other problems that they were looking at.